Okay, so I'm just going to do one or two videos on the string equation for this week. But remember, we are dealing with an equation, so I'm going to look at the very generic version of the string equation. So we've got m times the double t derivative of u is equal to the x derivative of k times the x derivative of u. And so here I want to include the possibility that m and k could be not constants. And then we have the assumptions u of x0 is equal to some given function f of x, and the t derivative of u evaluated at x0 is equal to some known function or some given function g of x. And so we have two spatial derivatives, we do have two spatial derivatives. Since we have two time derivatives, we would expect to have two initial conditions, which is very analogous to what you see in your ordinary differential equations class. You just imagine fixing a point x. For that point x, we have a second order differential equation in time, and so to get a solution we need, or to get a unique solution or something like that, we need both the initial position and the initial velocity. Now, one thing that we're going to assume, so I want to prove a statement about uniqueness. So I want to make this sort of ancillary assumption here. So I want to assume that there is some number, I'm going to call it r sub t, but because it's going to depend on time, there's some number r sub t such that u of xt is equal to 0, like identically equal to 0 for the absolute value of x bigger than rt. So what we're saying here is that our solutions have compact support. Now, that might seem like a big assumption. Why would we assume that? Well, remember we have this finite propagation speed. So if f and g have compact support, then as those disturbances travel through the string, our solution is only going to have compact support. So if I start with an initial hump and let it go, well, it's going to take a finite amount of time for that information to reach, down the string, or to travel down the string. So for any time, there's going to be, at some point, for any time value, no matter how fast this wave is traveling, at some point after that, okay, the string is going to be equal to 0. Another way to assume something like this is if we have a string and then clamp it down at 2 points, and we move it here, it's not going to affect what's happening over there. We'll talk. That introduces some new things, and we'll talk a little bit more about that in the second part of the course. But we're going to make this ancillary assumption here, which, like I said, is a physically reasonable assumption if we know that f and g are both functions of compact support. And there's varying degrees of detail that we can use to justify this assumption. But for now, I think I've justified it enough, or at least as much as I want to justify it. Okay. So I want to compute the total amount of energy in the string. And remember, energy is either kinetic energy or potential energy. The kinetic energy is 1/2 mass times velocity squared. So for the string, the kinetic energy at time t is just going to be the integral from minus infinity to positive infinity, 1/2 times the local mass of the string, which is going to be m of x times dx. M of x is mass density times dx, that gives us mass. And then the velocity is just the t derivative, like that. Okay, and let me write the argument here explicitly. This is t of xt squared dx. Okay, now for potential energy, you might remember that if you have a spring, the potential energy stored in a spring is equal to the potential energy stored in the string is the magnitude of the force needed to stretch a spring times the displacement. X here is the displacement. But by Hooke's law, this is equal to k times the displacement. Force is equal to k times the displacement. This is displacement from neutral, and then times this x here, and we can just write this as k x squared. Sorry, there's a 1/2 here. Okay, there's a number of ways to think, but you might remember in your there's a number of ways to see where this comes from. You might remember in your calculus class, you computed the work to stretch a spring from neutral to whatever position that it's at now. That's what this is here. Okay, your integral is an integral. It comes from an integral because what you integrate is something like 0 to x, if it's positive, negative, if it's negative displacement, k times s ds, and k here is a constant, and this is exactly what you get when you do that integral. This is the work done to stretch the spring, and so that's the potential energy. Okay, in the case of a string, it's not the displacement here is going to be the x derivative, because remember, the more we bend the string up, the more the force is going down or coming up if we bring this string down. So instead of x, it's going to be the x derivative squared, because that is what we're doing force against, and k is going to be this k right here. So the potential energy in this string is the integral from minus infinity to positive infinity, 1/2 k of x times the x derivative squared dx. Okay, so the total energy is going to be the sum of these two. So E of t is going to be the sum of these two things here. So I'll just put the 1/2 on the outside, minus infinity to positive infinity times this first part. And I'm not going to be able to write the argument, otherwise it won't fit on the screen here, or on the board here. So it's times mass times the t derivative squared plus k times the x derivative squared dx. Okay, so my claim that I want to write here is that under these assumptions over here, and assuming u is twice continuously differentiable, my claim is that energy is conserved. In other words, the derivative of energy is equal to 0. So that's my claim. Okay, and how am I going to do that? Well, I'm going to differentiate, which I guess is pretty obvious since my claim is a statement about the derivative. So if I differentiate this on the left-hand side, I'm going to get e prime of t. Okay, now when I do the differentiation, you'll see why I'm not writing the 1/2 in just a moment. I've got the integral from minus infinity to positive infinity. By assumption, the u is compactly supported and it's continuous, and its derivatives are continuous, so I can move the differentiation inside the integral here. Remember, m and k both depend on x, but they do not depend on t. So what I'm going to do is, m is a constant as far as t is concerned, so I've got to look at this part right here. It's going to be 2 times that 1/2, so that's going to go away, times the t derivative of u, and now I need to take the derivative of the inside, and that's going to give me the double t derivative. Something similar over here is going to happen. K is a constant as far as t is concerned. When I do the derivative here, I use the chain rule. The 2 times the 1/2 is 1, so it's going to be the x derivative of u times the xt derivative. Okay, so I'm not going to rewrite this line here, but I am going to note the fact that m times the double t derivative, m times the double t derivative is equal to this right here. So I'm going to get rid of that, and we're going to have the t derivative of u still, times the x derivative of k times the x derivative of u. All right. Now I need to somehow use this this PDE here again, and what I'm going to do is, or not this PDE again, I've already used the PDE, but I need to somehow, my goal is to show this is equal to 0. So I start to look here, I've got a t derivative and an x derivative. if I move the x derivative from here to there, I get a tx derivative, which matches with that, and then that'll leave me with a k partial xu, which is what I have there. So in other words, I want to use integration by parts to take this derivative and put it there. So unfortunately, I'm going to have to overload notation here, but using the standard notation for integration by parts, this is like my u, and so this part is like my v prime. Okay, but the u and that u are not the same. It's just the integration by parts u. Okay, so now based on this assumption here, that u is identically equal to 0 for some x bigger than rt, what this tells us is that the boundary terms in the integration by parts are going to be equal to 0. So we're just left with the non-boundary terms. So it's going to be writing this integral still. There's going to be the integral from minus infinity to positive infinity, but it's the integral of minus v times u prime. Okay, so it's going to be minus, what are we going to get? Well, I'm going to put the x derivative there, so it's going to be the tx derivative of u times, I'm going to take the derivative off of that, and so it's going to be k times the x derivative of u, and then I'll just have what I have over here, which is plus k times the x derivative of u times the xt derivative of u dx. Okay, now since u has second order continuous derivatives, it means the mixed partial derivatives are equal to each other. So the tx derivative here is the same as the xt derivative there, so I'll just change that to xt, and now these two things are equal. So this, those two functions are negatives of each other, so we're integrating a function that is identically equal to 0, and so what we get there is 0 as well. Okay, so what we've shown is that if u is a function that is twice continuously differentiable, it satisfies this problem here, plus this ancillary or auxiliary condition or side condition there. We've proven that energy is conserved. And of course, this is a sort of thing that we would expect in a so-called physical situation. We'll do something a little bit different. We'll do a very similar calculation in the second part of the class when we look at the string equation on a finite interval. Okay. So how can we use this? I'm going to give a very rough outline on how we can use this to prove a uniqueness theorem. So under the same assumptions, so I'm just going to write this. So this is a theorem. Under the same assumptions, in particular, this PDE and this side condition here, under the same assumptions, there is at most one solution. Okay, so under these conditions, there's at most one solution. Okay, and I'm going to use, and we can actually make this a little bit stronger. Let me actually say what there's more than one solution to. There's more than one solution to the following problem. I'm going to write the non-homogeneous version. So m times the t derivative of u minus the x derivative of k times the x derivative of u equals h. Okay, and here h can depend on both x and t. And we've got u of x 0 is equal to f of x, and the t derivative of u of x 0 is equal to g of x. There's at most one solution to that problem there. Okay, so like I said, I'm going to give a very rough outline to this problem, or to this theorem, and you can use, I want you to think about it. So here's the proof. Okay, so whenever we're proving a uniqueness statement, one way to do this is to say, let's assume we have two different things and show that they're equal to each other. So I'm going to say, assume u is a solution. Actually, I'll say, assume u1 is a solution, assume u2 a solution. I want to show that u1 is equal to u2. Well, one way to show u1 is equal to u2, especially when you're dealing with a linear function like we have here for the wave operator, is to show that u1 minus u2 is equal to 0. So let u1 and u2, sorry, I want to explicitly add this and condition that says u of x comma t is identically equal to 0 for the absolute value of x bigger than RT. It's just this condition. Okay, it's just the compactly supported condition. So let u1 and u2 solve the above. And we're going to set w to be u1 minus u2. So we're going to set w to be u1 minus u2. Okay, so we're going to set w to be equal to u1 minus u2. Then w solves the homogeneous equation of the above. Then w solves the homogeneous version of this equation. That is, h is equal to 0. Okay, that's something that you're going to have to explain why. So, I'm going to say E sub w of t, that's the energy, so E sub w of t is constant. So when I say E sub w means the energy integral, but with w in there instead of u. So that's constant because we just proved that if a function satisfies, if a function satisfies the homogeneous wave equation, then we have these other side conditions, then energy is conserved. So this is constant, but actually we can say something a little more. We can say the energy in w at any time, the energy in the string at any time is equal to E of 0. Okay. We see that w of x0 is identically equal to 0, and the t derivative of w of x0 is identically equal to 0. Again, that's something that you're going to have to reason through and explain why. So, this says energy of w at time 0 is equal to 0. Again, that's something you're going to have to explain. Thus, the energy at any time is equal to 0. Which the t derivative of w at any time is equal to 0. And this is for all x. Again, you're going to have to explain that. And because of that, we know that this should say w of xt. You know that the t derivative of w of xt is equal to 0 for all x. That's something you're going to have to explain. And because of that this says that w of xt is identically equal to 0 for all x and t. Actually, I will say this. I will say something a little more specific here. W of xt, or sort of show you one of the steps. W of xt is equal to w of x0 for all x. So, and again, you're going to have to make this step connection going from there to there. So w of xt is identically equal to 0. And if w is equal to 0, it means u1 minus u2 is equal to 0, and u1 is equal to u2. Okay, so this is a energy theorem and an existence theorem for the string equation. Obviously, I think they're both independently interesting. I think it's good to show that the string conserves energy, that energy is conserved, right? That sort of indicates that we have this mathematical model, sort of indicates that our mathematical model is internally consistent with how we think about physics and energy being conserved and things like that.